Our next problem is probably the most involved in terms of the sample problems that we're going to do. It's just going to take a little bit of time to go through it, but conceptually I think it's pretty easy to think about. Remember when I gave our introduction, before I talked about sample problem 9.1, we've got 3 ways now that we can think about delta H of a reaction if we want to figure out what it is experimentally. I shouldn't say experimentally, some of these are empirical methods, but for example, we can use Hess's law. And we can basically have a laundry list of equations that we just kind of sum up and manipulate to get our overall equation. We can have delta H of formation, so we can use appendix B and values from that to kind of determine the enthalpy of a reaction. And in this way, we're going to do something kind of similar here, where basically what we're going to do is we're going to say, you know what, we're going to break apart every single bond in our reactants, and then we're going to reform every single bond in our product. Keep in mind, and it's important to say this is not what happens in real chemical reactions. But from a thermodynamic standpoint, from an energy standpoint, we can do this treatment to get at the enthalpy of the reaction. So what we're going to do is we're going to think about breaking every single bond in our reactants, and these are going to be what we're going to refer to as costs. We're going to call them costs because it takes energy to break bonds. So what that means is we're going to have a positive delta H from this process. When we form bonds, we're going to think about these in terms of gains. We get back energy when we make bonds. And if you remember in class, we talked about when you have 2 nuclei that come together, as they start coming together and their electron clouds overlap, and again, this is for covalent bond formation, that becomes stabilizing. And that becomes a species that's lower in energy. And so if we start with something that's higher in energy and we end up with something that's lower in energy, the energy difference must be given off to the surroundings. And so anytime we make bonds, that is going to be something that gives us back energy. So those are going to be gains. So we make energy when we make bonds. And so that is going to be a negative delta H, remembering that negative delta H's are exothermic reactions, meaning that that excess energy is given off from the system to the surroundings. So basically what we need to do is just kind of figure out, you know, breaking every bond here, and that's going to be a positive enthalpy, forming every bond here. So this basically is going to be a lot of use of table 9.2. It's a little bit hard to see here, but again, you're just going to look up whatever this bond is, and you're going to write down the energy value. This is the energy value for 1 mole of those bonds. So at times we might need to consider stoichiometry with this. Okay, so what we're going to have here is I'm just going to write down for my reactants, I'm just going to start tallying up all of these species. And I already have figured out what my numbers are, so I'm not going to keep referring back to table 9.2, but make sure that you are able to look at table 9.2 and see where I get all of these numbers from. So again, my reactants, we're going to have costs associated with these reactants. I shouldn't have quotes really around reactants here. The quotes goes around costs. All right, so I've got 4 carbon-hydrogen bonds. So 4 carbon-hydrogen bonds means I'm going to take 4 times the value of each carbon-hydrogen bond, which is 413 kilojoules per mole, and I'm going to consider that I've got 4 moles of those bonds, and that equates to 1,652 kilojoules. Okay, we've got a Cl-Cl bond in this, but again, my stoichiometry has to come into play, and so I'm going to need to have 3 of those. So I'm going to have 3 times 243 kilojoules per mole, and that equals 729 kilojoules. So when I add this up, the delta H for breaking bonds is equal to 2381 kilojoules. So again, I'm going to have these noted as positive values because I know that it takes energy to break those bonds. When I think about my products, again, I'm going to think about these as gains. And what I'm going to do is I'm going to automatically change these to a negative delta H value. I used positive delta H values for my reactants because I knew I was breaking those. I'm going to automatically make a negative delta H for my products because that's energy that I'm getting back. So again, looking at what we make here, we're making 3 of these carbon-chlorine bonds. So 3 carbon-chlorine bonds means I'm going to have 3 times minus 339 kilojoules per mole. And again, I'm adding that negative in just mentally, right? It's not what I get off the table. I'm just making that a negative because I know that that is a bond that's being formed. So that gives me minus 1017 kilojoules. And again, you'll see this come into play here. I'm going to have 1 carbon-hydrogen bond. So here's a carbon-hydrogen bond. Okay? I imagine breaking it on the left side and making it on the right. So I'm going to have 1 then times minus 413 kilojoules per mole. Note, that's the same number that I have there. All I've done is change the sign because I'm considering that to be a bond that's being formed. So this is again minus 413 kilojoules, and I'm going to have 3 of these HCl bonds that get made. So 3 HCl bonds, so that's going to be 3 times minus 427, and that's equal to minus 1281 kilojoules. So the delta H for making my bonds and my products is negative 2711 kilojoules. Now, with this equation, because it's adding these together, you don't have to remember, well, is it this minus this or this? No, you're adding things together, and we automatically accounted for the fact that making bonds gives us back energy. So all we need to do is add these 2 up together. So delta H of a reaction is equal to positive 2381 kilojoules plus my negative 2711 for energy that I get back. And so overall, my delta H of my reaction is minus 330 kilojoules. So again, this tells me that my reaction is exothermic, and I would expect heat to be given off from this reaction.